Hi everyone, we're starting with atoms today. What is an atom? It's the smallest unit of an element that maintains its chemical identity. So if you start breaking up the atom into even smaller particles, which we do know that an atom can be broken into smaller particles, but if we do that, it's not the same thing anymore. So to maintain that chemical identity of that substance, atom is as small as you can go. What is an element? It is a pure substance that you can't separate into anything more simple. You can't make it any smaller. It's all one atom type. It's all uniform. And you can't break it down into anything that is more simple. It's all made of the same type of atom. So if you have silver, silver is an element. Pure silver contains only silver atoms. We've got a little biology tie-in here. We've got the most abundant elements in the human body. There is more than just what is on this list, but they are in very small amounts. This kind of hits the high points. Our most abundant element, of course, you can see here, is oxygen. Our second most abundant is carbon. That's why in sci-fi they talk about carbon-based life forms, because as far as we know, all life is very carbon-based. That's our experience here on Earth. Next comes hydrogen, and lastly comes nitrogen, as far as the bigger pieces of the pie there. Nitrogen is a very important part of DNA, for instance. It's one of many things. Then we have a bunch of other smaller pieces there. We have calcium, sodium, potassium, magnesium. These are what we would often refer to in our day-to-day lives as the electrolytes. So we need to go drink a Gatorade or go drink a Powerade to replace our electrolytes. You can see there that they're much smaller percentages of the human body, but they're very, very, very important. Without the proper electrolytes, our muscles don't work, our nerve signals don't work, brain won't work. So those are all very, very important, even though they are in smaller amounts. So these are all elements that are in the human body. Okay, here's a list of elements that can be found in the human body. You can see there's many more than were on that pie graph. And it says there at the bottom that scientists have discovered that the human body is comprised of some 29 base elements and trace elements. Okay, so the ones listed here in bold are definitely or very likely essential for life. So if we don't have these, we're in danger. Okay, and all of these are also found in the earth. So 95% of our bodies have the elements that are found in the brackets, those first four: oxygen, carbon, hydrogen, and nitrogen that we've already mentioned. But yet, as you can see here, there are a lot of other things that can be found in the human body. The other ones that aren't in bold, we don't know for sure if they're essential for life or not, but they have been found in living organisms. Okay, we're going to look at some basics of the periodic table. We'll get more into the periodic table later, but we're going to look at some basics as they have to do with atoms and elements. So firstly, here we have atomic number. Okay, so this atomic number is right here. Okay, 12 is the atomic number for magnesium. And this number is specific to a specific element. So magnesium will always, always, always be number 12 on the periodic table. Okay, it identifies the element. The chemical symbol is this right here. Chemical symbol just means the abbreviation. Okay, some periodic tables don't have the full written out name of the element. Some just have the symbol. Some of them do have the name. The periodic tables you will get in class will have the name as well. But it's a good idea to get familiar with the symbols themselves. Makes it a little faster and easier to find what you want on the periodic table. Okay. These are the abbreviations from the periodic table for very common elements that you want to start committing to memory. And there's a reason for this. It is because these are ones that are, like I said, common, but also very easily confused with other, some of them are easily confused with other elements. I know you can do this because you have a lot of abbreviations that you have memorized for all of the messaging and texting and whatnot apps we have nowadays. But let's look at some examples here. Let's look at the first two, sodium. So if we were to be logical, we would think sodium, the abbreviation or the chemical symbol, would be what? Maybe S, maybe SO. But we would think it would be something like that because of the word sodium. Sodium is actually Na, which is Latin natrium, Latin for sodium. The reason we don't use S, just as an example, okay, S is sulfur. S is sulfur. So if we had S for sodium and S for sulfur, how would we tell the difference between those two? Potassium, we would think would be P or PO. Unfortunately, doesn't work because P is phosphorus. Okay, PO is polonium. So they ran out of letters of the alphabet. Even in many instances, they ran out of the combo of the first two letters. So they had to get creative. So the vast majority are English, so to speak, names of these elements. Some of them come from the Latin words. That's the most common. There are a few from German as well. Okay. I've told some of you probably, but lead, the PB of lead comes from the Latin plumbum. Plumbum is where we get our terms for plumber and plumbing. And the reason that we have those words plumber and plumbing is because the first plumbing, the first pipes back in ancient Roman times, were made from lead. And the theory is that many of the Roman rulers, the rich people and the people in charge, they had the money to have water piped to their homes, so they had indoor plumbing, and they were drinking water from these pipes, and it is believed that many of them had lead poisoning, which was why they were crazy. Okay. Compounds is our next vocabulary term. Compounds are sometimes referred to as molecules, although molecules are a very specific type of compound, but sometimes we get lazy and we use them both interchangeably. Okay, but we're starting to put atoms together. We might put two of the same atoms, two different atoms, three or more atoms, but we're putting atoms together. We talked about the most abundant element in the human body was oxygen. What do you think the most abundant compound in the human body is? If you said water, H2O, you were right. Okay? Water is the most abundant compound in the human body. So a chemical formula, example we have right there, H2O, chemical formula or a molecular formula, just tells you the amount of each kind of atom that are stuck together to make a particular compound. Okay? I just want to mention, we do have a few molecules that we call the diatomic molecules, di meaning two. There's a way to remember these. I'll show you here in a moment. I call these the lucky seven. So you'll hear me refer to them as the lucky seven quite a bit. There are 7 total. So if you count what we have there, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, there's 7 total. And you see there that each one has a little 2 after them. So in nature, these atoms do not exist by themselves, or they're not represented as existing by themselves. They always, always, always have a buddy in nature. They work off the buddy system. Okay. So here you can see our little cheater way to remember this, to memorize this, the 7 diatomics. Okay. We start at number 7. So nitrogen, the atomic number for nitrogen is number 7. It's always number 7. So we start there. Nitrogen. And then we draw a 7. So you can see the 7 there drawn on the periodic table. Start at 7, draw a 7, and then the 7th is hydrogen. So you have to come over here to this side and pick up hydrogen. Okay? Start at 7, draw a 7, the 7th is hydrogen. These are our diatomic. Okay, let's look at a compound or chemical formula and assess what it's telling us here. So we have the chemical symbols. The first one we have here is a C, and C is carbon on the periodic table. You can look up and find C, and it is carbon. The second letter is oxygen. So if you look up capital O, that is oxygen. Okay. If you have a second letter, so if one of your abbreviations, your chemical symbols, has a second letter in it, the second letter is always lowercase. Okay, so this is going to become very, very important whether you write uppercase or lowercase. So if I wrote uppercase C and lowercase o, that's cobalt. Uppercase C and uppercase O is completely different from uppercase C and lowercase o. Seems picky, but it's an entirely different chemical. Okay, in this case, we even have a compound versus an element. So this number down here tells us we have 2 oxygen. Not 2 of the whole thing, but 2 oxygen. Why? Because the 2 comes right after the O. And we call this a subscript. Okay, subscript. So it only says how many of the element it comes directly after. Technically, we just have 1 carbon, but we don't usually come in here and write a 1 like this. We don't say C1O2. It doesn't work that way, okay? So if we were to count the atoms in this particular chemical formula for carbon, how many carbon atoms are there? There are 8. How many hydrogen atoms? 18. We just look at the number that comes directly after the element. Pretty easy. Okay? A chemical reaction or a chemical change just means that we're rearranging the different atoms. We're breaking apart some atoms, we're putting them together in new ways. That is a chemical reaction in essence. And when we have these chemical reactions, we have to conserve the mass. It's called the law of conservation of mass. We cannot create, we cannot destroy, only God has that power. It goes against the laws of nature. We cannot do it. Okay? It can turn into something new and different, but we can't just make it appear from nothing. Atoms can't appear from nothing, and we can't just make them disappear completely. It does not work. So this is a law. Nobody's going to dispute this law of conservation of mass. Has to come from somewhere, has to go somewhere. And if you look at the pictures, this is just some examples here of chemical reactions. Look at the pictures here. You can see, okay, that we're have the same amount of dots, if you will, on each side of the arrow. So in the first example, we have 2 blue and 1 red. They attach together to make 2 blue, 1 red. They've been rearranged, they're attached together differently, but we still have the same stuff there. We still have the same atoms. You should be able to see that in each one of those. Okay. And then atomic mass unit, and we're going to be calculating some of these. Atomic mass unit, they define it as 1/12 the mass of a carbon-12 atom. Okay, so carbon is atomic number 6. It's always 6 on the periodic table. And 6 tells us how many protons it has. All right, and then the most common form of atom also has 6 neutrons. So in the center of that atom, we have 6 in one particle, 6 of the other, so we have 12 total. 6 by 6 is 12. And so if we take 1/12 of that, then essentially we're taking the mass of just one of those particles in the nucleus. Okay, so this is just how they defined what an atomic mass unit is. So when we're calculating these, we're calculating them for one atom. We're referring to one atom. We're doing these calculations, and it's just strictly adding together basic numbers. It's really not that hard. Okay, so we're going to mention the periodic table, so we're going to talk about the first classification. Very beginning of the Bible, what do we start out with? Pretty much right off the bat, as soon as man is in the picture, God tells man to name the animals. We are designed to try to classify our environment and to put things in order to try to understand our environment, okay? And we believe as Christians that this gives glory to God when we do this. So what have we done? We've done this with chemistry, with the elements, as we've discovered these, and we'll talk about the evolution of the periodic table, but you can see it's very organized. A little bit of a weird shape, but we do have nice rows and columns and an organizational type look to this. This particular one, it even has some color coding to it. And so we took a lot of different things and we use those to organize the elements. So reactivity is just one property that we use to organize the elements in the periodic table. Reactivity just means how well will something combine with something else. So how well will that atom interact with other atoms? Okay, and this is one of many things that we use. Okay, so as we discovered the elements, there were approximately 70 discovered or known by 1870. These were the really common ones that you probably think of, particularly a lot of the metals, silver and gold and copper and zinc and nickel, and ones that we've known for thousands of years. Okay, and during the Industrial Revolution, we started in the 1900s, we started having a lot more equipment, a lot more machines, a lot more ability to do more testing and to discover new things about elements that we already knew about and even about new elements themselves. Okay, and we kind of went through an evolution. We had some different chemists come up with some different ideas, and this one chemist, Mr. Newlands, he discovered the periods of the elements and called them octaves because he noticed a repetition. Just like in music, we say A, B, C, D, E, F, G, A, B, C, D, E, F, G, A, B, C, D, E, F, G, and then we do that, we call them scales, we do that in music. Similar sort of thing he saw in elements, okay? And so we started to put this periodic table together, and Mendeleev is the guy that is predominantly given the credit for coming up with the periodic table that we have today. And you can see a picture here of Mendeleev, and this is actually a copy of one of the first periodic tables that he came up with, which obviously doesn't look anything like our periodic table today. If you look really closely and compare it with the periodic table, you'll notice that those numbers are not the atomic numbers, the ones that go in order on our periodic table today, but they are actually the mass, or how much matter is in each element. But he started seeing all these different connections, and he was the one that you'll notice some question marks on there, you'll notice some blanks or some gaps. And Mendeleev was the guy that said, you know what, we see this pattern here, but we have an element missing. So I predicted that there is an element that goes here that we haven't discovered yet. And so he was able to help scientists discover a lot of new elements. Okay, Moseley changed the periodic table from mass to number of protons and how it was organized. So he used the atomic number Okay, notice this was just in the 1900s, so we're talking a little over 100 years ago. And we have a thing called a periodic law, which just says there are repetition of properties in the periodic table. So why do you go across a row and then you go down to the next row and start a new row, and you go down to the next row and start a new row? Because of this repetition of properties of the elements. Okay, this just kind of shows on a timeline how we came up with the octaves, and we came up with as we go down the Mendeleev's periodic table. One we didn't mention there at the top was the triads. Another scientist, Dobereiner, was seeing some repetition and some patterns. So all of these people, these scientists, were seeing the repetition, and they just kept adding to the knowledge, and we kept fleshing out the periodic table to what we see today. Okay, here's some ways besides reactivity, ways that we have the periodic table categorized. We categorize elements by metals, nonmetals, and metalloids. Metalloids are kind of like fake metals, if you will, or they're halfway in between metals and nonmetals. And so this periodic table is color-coded, and you can see there that the really light green look, those are the metals. And most of the periodic table are metals. You can tell that there. The vast majority are metals. Then we have the yellow ones, the bright yellow, which is the nonmetal. Okay, small chunk are nonmetals. And then right there where the stairs are, we call the stair step. You can see looks like stairs drawn right through the periodic table. Some of the elements right there along those stairs are metalloids. The metalloids' claim to fame is those are semiconductors. So if we didn't discover the really cool properties of metalloids, we would literally not have computers today. That has allowed us to have the computer chips that we have today that are in our phones and in our laptops and other things. Those circuits are predominantly made from metalloids. They are partial conductors of electricity, but they don't heat up as much, because if we used metals and tried to make really, really tiny little circuit boards, the metal would heat up and it would melt and it would fry the circuit board immediately. So this is the claim to fame of metalloids. Okay. This is another color-coded periodic table that shows different properties. So in their natural state, that means in nature, naturally, if they exist in nature in the elemental form, would they be solid, liquid, or gas? And I know you guys know what a solid, liquid, or gas is. So most of the periodic table, because most of them are metals, they exist as solids. You can see the white there is solid. There's only two things that exist as a liquid under natural conditions on Earth. That's bromine and mercury. And then you'll see a few that exist as gases over there in yellow. Some of those are really obvious, like oxygen. I mean, we know that oxygen is a gas, right? Pretty easy stuff. Okay. And so when we have elements or we have chemicals that are in particular phases of matter, so solid, liquid, and gas, oftentimes we represent those a particular way. Okay. So let's look at this first one here. I have water on here a bunch of times, H2O. This first one is solid water or ice. And so if we were to represent that, we would put an S for solid in parentheses. Because water can be in a lot of different states, sometimes it's helpful to know, well, is this ice, is it water, or is it steam? So liquid water would be an L. It's supposed to be a cursive L there. L for liquid, and a gas would be a G for gas. So easy enough. We can designate what state of matter that particular chemical is in. We have another one, though. This is not really a state of matter, but in chemical reactions, oftentimes we have things that are dissolved in something else. So we wouldn't normally do this with water, because water is aqueous, because it's water. That's what aqueous, the definition of aqueous is. But we can also put parentheses in AQ for aqueous. And what that tells us is normally this is going to be on something like a salt. Like this is table salt here. Okay, and it tells us that that table salt is dissolved in water. So it's not in its solid form like a little crystal salt in a salt shaker, but it's actually been dissolved in water. And sometimes for chemical reactions, it's important to know whether it's in its solid form or it's a salt that's been dissolved in water. So we use that aqueous, just means, oh, guess what? It's in water, guys. We dissolved it in water. Okay. So our modern periodic table, we have rows and columns, and we do give those names. So if we're looking at the vertical columns, the vertical ones are groups or families. That's our vertical columns. Okay, vertical columns are groups or families. The horizontal rows are periods. And so you'll see there on the left, right here, we can see 1, 2, 3, 4, 5, 6, 7 going down. Our periods are just numbered. So the very first row that just has the H and the HE, that's row 1, period 1. And they just go down from there. The groups or the families, those are our vertical columns. Many of those have names, and we will be learning those names. Okay? Many of them have special names. But periods are easy because they're just numbered. And that is all I have for you today. Thanks for being with me.